Hello everyone, welcome to my class. In today's class I am going to cover solving a linear system using matrices. So let me start the class right away. First, let me give you a definition of matrix. A matrix is a rectangular array of numbers. The numbers are called entries or elements of the matrix, arranged in horizontal rows and vertical columns. Matrix is denoted by capital letters and is written by enclosing entries by the bracket or the parenthesis. A matrix is referred to by its size. For example, size m by n indicate that m is rows and n is columns. For matrix A, each entry in the matrix is referred to as little aij in A. This belongs to sign, where I represents rows and j represents the columns. Quick example of matrices. Here the matrix A of size 1 by 2. So here there are 1 rows and 2 columns. The matrix B is of size 2 by 2, 2 rows, 2 columns. Always rows are horizontals and columns are verticals. Similarly, matrix C is of size 2 by 3, 1 rows, 2 rows and 3 columns, 1 column, 2 column, 3 columns. And the entry here, the 1 is denoted by, in this notations, A11. That means row 1, column 1. Similarly, the entry 3 in matrix B is denoted by B21. B21, here the 2 implies row 2 and 1 implies column 1. Similarly, the entry 6 in the matrix C is denoted by C23. This 2 here, 2 implies second row and 3 implies third columns. Great. Next, let me give you some other definitions of matrices. Square matrix is a matrix which has the same number of rows and columns. Row matrix is a matrix which has only one row. Column matrix is a matrix which has only one column. Matrix addition and matrix subtractions. We add or subtract two matrices if they have the same dimensions, and we perform the addition and subtractions corresponding entry wise. By the way, the matrix addition is commutative and associative. Next, a scalar multiple of a matrix. A scalar multiple of a matrix is done by multiplying each entry in the matrix by the scalar. For example, our matrix A is 1, 2 and C is a scalar. When you multiply the matrix A by the scalar C, then we multiply each entry by the scalar. So we have C times 1, C times 2. So the new matrix is CA, which is C twice C. I hope this makes sense to you all. Next, diagonal entries. For square matrix, the values on a diagonal line from upper left to the lower right are called the diagonal entries. For example, in the following matrix K here, in the following given 3 by 3 matrix K, this is the diagonal line. So the diagonal entries are 3, minus 2, 5. I hope this makes sense to you all. Next, quick note. A matrix can be used to represent a system of linear equations as well as solving the linear system. In such cases, the entries represent the coefficients of the variables and the constants in the system. When solving the system using matrices, much of our focus is on the diagonal entries. Triangular matrix. A matrix is said to be in triangular form. So here by triangular we mean upper triangular form. if all the entries below the diagonal are zeros. For example, in the given matrix D here, this is the diagonal line. These are the diagonal entries, and below the diagonal entries, elements are zeros here. So this is called upper triangular form. Augmented matrix. An augmented matrix is a matrix obtained by adjoining the coefficient matrix and the constant matrix of the system. Quick example. Here, given system is a 3 by 3 system, 3 equations, 3 unknowns. Unknowns are x, y, and z. And the coefficient matrix are the matrix found by the coefficient of the unknown variables. Here, the coefficients are 3, 1, 1, 3, 1, 1. Similarly, from the second equations, 1, minus 2, 3, 1, minus 2, 3. Similarly, from the third equations, the coefficients are 2, minus 3, 5, 2, minus 3, 5. So this matrix is called coefficient matrix. Similarly, the matrix formed by the right hand side of the systems, this constant, are called the constant matrix. Here, minus 2, 1, 3. And the augmented matrix is found by adjoining these two matrices, coefficient matrix and constant matrix, and we write in this way. So this is the coefficient matrix and this is the constant matrix, and here this vertical line corresponds to the equal sign in the systems here. These are the coefficients of unknown variables in the systems, and this is the right hand side of our systems. I hope it makes sense to you all. Next, the conversion chart. So in this previous example, we formed the augmented matrix from the system of equations. So now, if the augmented matrix is given to us, then we can rewrite this augmented matrix in terms of the system of equations in this way. So here, in the augmented matrix, this is the coefficient matrix and this is the constant matrix, and then the first row corresponds to the first equation in the system, second row corresponds to the second equation of the systems, and third row corresponds to the third equation in the systems. So here, 3 times the x plus 1 times y plus 1 times z equals to minus 2, which is the first equation here. Similarly, 1 times x minus 2 times y plus 3 times z equals to 1, the second equation in the system. Similarly, here's 2 times x minus 3 times y plus 5 times z equals to 3. This is the third equation in the systems. So I hope you understand how to convert augmented matrix to the system of equations and from the system equations to the augmented matrix. Let's move on. Next, matrix in row echelon form. We also write matrix in RREF form. A matrix having ones down the main diagonal from upper left corner to the lower right corner and zeros in every position below the main diagonal is called the matrix in row echelon form. For example, in this square matrix, diagonal entries are 1 and below the diagonal entries we have zeros. Similarly here. Next, matrix in reduced row echelon form or matrix in RREF. So the matrix in row echelon form where the leading entry 1 in each row is the only non-zero entry in each column. So that means if you have the main diagonal entries are 1 and all other entries are zeros, then this form of matrix is called matrix in reduced row echelon form. So here matrix K and matrix D are in reduced row echelon form. Now next, let me give you a comparison chart between square matrix, matrix in row echelon form, and matrix in reduced row echelon form. So here K is the square matrix. Its size is 3 by 3, 3 rows, 3 columns. And next, this is the matrix in row echelon form, where diagonal entries are 1 and below the diagonals we have zeros entries. And the third one here the diagonal entries are 1 and all other entries are zeros. So this is the matrix in reduced row echelon form. I hope this makes sense to you all. Quick remark: we perform elementary row operations, that is, interchange rows, multiply a row by a constant, add any two rows and the sum used to replace one of the rows to convert the coefficient matrix to the row echelon form. Any equation with an x coefficient of 1 can be made row 1 in elementary row operations. Also note that elementary row operations correspond to manipulating the equations in the system. Quick recall: the back substitution technique, the process of finding the unknown variables from a system in an upper triangular form, is called the back substitution technique. We studied the back substitution technique in our last class. Now let's move on. Next, triangularizing the augmented matrix, that is, how to convert the augmented matrix in upper triangular form. Here are the steps to remember. Steps: first, write the system of equations as an augmented matrix. The augmented matrix is a matrix formed by adjoining coefficient matrix and the constant matrix. Step 2, make sure the first row has the leading entry 1, else interchange rows if necessary. Step 3, use elementary row operations to obtain zeros below the diagonal entries and continue until the matrix is an upper triangular form. If any rows contain all zeros, put them at the bottom of the matrix. Step 4, convert the upper triangular matrix form back into the corresponding system of equations and solve by back substitutions. Again, we learned back substitution technique in our previous class. Next, quick remark: the triangularizing process is called the Gaussian eliminations method if the final matrix is in the row echelon form, and it is called the Gauss-Jordan elimination method if the final matrix is in the reduced row echelon form. I know there are a bunch of definitions. Now, one more: inconsistent system versus dependent systems. When solving the system using matrix method, if all entries in a row of the coefficient matrix are 0, then the system is inconsistent system. If all entries in the last row of the augmented matrix are 0, then the system is called the dependent system. Great. Now we are ready to do some example. Now let's begin the example. Example 1. Given a system of equations in 3 variables, answer the questions part A through D. So here given system is 3x plus y plus z equals to minus 2, x minus 2y plus 3z equals to 1, 2x minus 3y plus 5z equals to 3. So the first sub questions, part A, write the coefficient matrix of this system, the constant matrix of this system, and form the augmented matrix for the systems. So let's begin the solutions. So the coefficient matrix is the matrix formed by the coefficient of these unknown variables. So here is a 3, 1, 1 is the first row of the matrix. For the second row, it comes from the second equations here. 1 minus 2 3, 1 minus 2 3, and similarly the third row of the coefficient matrix, the entries are coming from the third equations here, the coefficient of the unknowns, 2 minus 3 5, which is here. I hope this makes sense to you all. Next, the constant matrix is the matrix formed by this right hand side constant of the system, so it's a minus 2 1 and 3. And finally, the augmented matrix is the matrix formed by adjoining these two matrices, coefficient matrix and the constant matrix, and we write in this way. This is the coefficient matrix, this is the constant matrix. Great, I hope this makes sense to you all. Now let's move on. Let's do part B. Perform row operations and reduce the augmented matrix into the row echelon form. So here, the augmented matrix is here. Right? So now we want to reduce this augmented matrix in RREF form. So that means we want the diagonal entries ones, and below the diagonals we want a 0 entry. So here 0, here 0, and here 0. In the diagonals we want ones. So now let's begin. So that's better. So now first we want first non-zero entry 1. So we switch the row 2 and row 1 so that this 1 goes in here that we want. So here we switch row 1 and row 2. That's a row 2 becomes row 1 here now. 1 minus 2 3 1, and then row 1 becomes row 2 here. So 3 1 1 minus 2, and row 3 as it is, 2 minus 3 5 3. I hope this makes sense to you all. Now let me scroll this way. Yep. So the next we want to make zeros below the first diagonal entry. So we want 0 at the place of 3 and at the place of 2. Then how can we make zeros here and here? We multiply the row 1 by negative 3 and add to row 2 and replace the row 2 by that result. Similarly, to make 0 here, we multiply the row 1 by negative 2 and we add to row 3, and the result we want to replace the row 3. So then we will have 0 here and 0 here. So that's the idea. So here we replace row 2 by negative 3 times row 1 plus row 2, and we replace row 3 by negative 2 times row 1 plus row 3. I hope these operations make sense to you all. So now I explain here. The details is here. Here, multiply row 1 by negative 3. So here is the negative 3 times 1, negative 3. Negative 2 times negative 3, positive 6. Negative 3 times 3, negative 9. Negative 3 times 1, negative 3. And we copy the second row as it is. And we add them. And then this becomes our new row 2. Similarly, our new row 3 is here. We perform these operations. We multiply row 1 by negative 2 and add row 3, and we replace the row 3 by that sum here. Minus 2 times 1, minus 2. Minus 2 times minus 2, plus 4. Minus 2 times 3, minus 6. Minus 2 times 1, minus 2. We copy the row 3. 2, minus 3, 5, 3. We add them. Minus 2 plus 2 cancels. 4 minus 3, 1. Minus 6 plus 5, minus 1. Minus 2 plus 3, 1. So now this is our new row 3. This is our new row 2. Our row 1, we didn't do anything. We just copy the same here now. So the new matrix is same row 1 here from here. I use the different color so that it's easier for you to follow the steps here. So this is our row 2, which I copied here. and this is our row 3 copied here. So now what do we have so far? We have now this one here, the diagonal, this entry is 1 here, we have 7 here, we have -1 here. So we want to make diagonal entries 1, and below the diagonal we want 0. So we have 2 zeros already here, that's good. Now we want to make this one also 0, and we want to make this 1 at the place of 7, and we want to make 1 at the place of -1. So the next, to get zeros below the second diagonal entry, that means here, we want to make this one 0 here. We follow the following operations. We use row 2 minus 7 times row 3, and we replace the row 3 by this result. So here, let's perform here. So row 2 as it is, and we multiply the row 3 by -7. So -7 times 0 is 0, -7 times 1 is -7, -7 times -1 is +7, and -7 times 1 is -7, and we add them. So 0 plus 0 is 0, 7 minus 0 is 0, -8 plus 7 is -1, -5 minus 7 is -12. This is our now new row 3. So then let me rewrite what we have here. I'm just copying this first row and second row, and I'm replacing this third row by this row here. I hope you are following me. So here, first row as it is, second row as it is, and now this is my third row. Third row is here. Let me scroll this way. Yep. So now we are almost there. So then we wanted the diagonal entries 1s and below the diagonal 0s. Now we have all the entries below the diagonals are 0s. So that's good. So now we want the diagonal entries 1. So here we want 1. So that means we divide the third row by -1. So that gives me +1 here. That's fine. In the second row, we want to divide the second row by 7. And then that gives us 1 here. Then we're done. So consequently, the matrix in row echelon form is as follows. First row as it is. In the second row, we divide by 7. So then here is a 0 over 7, 0, 7 over 7, 1, minus 8 over 7, minus 5 over 7. And the third row here, we want to multiply by -1. So this becomes positive, this becomes positive. So this is +1, +12, 0, 0. So here's all we want the diagonal entries 1, and below the diagonal zeros, the other entries we do not care, whether plus or minus or 1s or 2s or fractions, we don't care. So what do we care? We only care the diagonal entries have to be 1, and below the diagonal we do need zeros entries. I hope this makes sense to you all. So now this final matrix is the matrix in row echelon form. We're done. So now in part C, reduce the augmented matrix into the reduced row echelon form, or in RREF form. To begin the solutions, so now in RREF we want the diagonal entries 1. Again, in RREF we want this diagonal entries 1s and all other entries 0s in the coefficient matrix of the augmented matrix. So now let's perform the following row operations subsequently from top to bottom. So now this is the augmented matrix given earlier. Let me show you here. This is the matrix we obtained here. Okay, let me scroll down again. Yep. So now first we want the first leading term is 1, so we switch row 1 and row 2. So here we perform switching row 1 to row 2. So that is Here's a 1, minus 2, 3, 1 becomes our first row. 3, 1, 1, minus 2 becomes our row 2, third row as it is. And then the next, we want 0 here. So to get 0 here, we multiply row 1 by negative 3 and add row 2 and replace the row 2 by this result. Then we will get this one here. Let me go over here. So here we multiply R1 means row 1 by negative 3. So this becomes minus 3. Add to 3. So now this is 0. So here we multiply minus 2 by minus 3. This becomes plus 6 and add 1, 7. Similarly, here in this place here, multiply 3 by minus 3. So 3 times minus 3 is minus 9. Add this 1. So minus 8 is minus 8 here. Similarly, multiply 1 by minus 3. So minus 3 times 1 is minus 3. And add this minus 2. So minus 5 we have here. And row 3 is as it is here. I hope this makes sense to you all. So next, we want to make 0 here. How do we make this 0 there? We multiply the row 1 by minus 2 and add row 3, and this gives me 0 here. So now perform these operations, then we will get here first row as it is, second row as it is from here. Now only third row changes here with these operations 0, 1, minus 1 and 1. So I want you all, please, actually you sit down and do the algebra here. And now let me move on. So now we are here. Okay, we have 0 here below this 1. So that's great. So next we want to make 1 on this diagonal entry here. So then we divide the second row by 7, first row and third row as it is. Next, we want to make 0 on this entry here, below this 1 diagonal entry. So to get 1, we perform this one. We just multiply row 2 by minus 1 and add to row 3 and replace the row 3 by this result. So this gives me here 0. Row 1 as it is, row 2 as it is, now row 3 changes. And now next step, we want this diagonal entry 1. So we simply multiply row 3 by 7. Row 1 as it is, row 2 as it is. Now row 3 multiplying by 7 gives me 1, 2 all. By the way, this is the row echelon form obtained in part B above. Okay, great. So now, what next? So next we want to make 0 here, 0 here, 0 here. Again, we don't care this constant matrix in the augmented matrix. We are only caring here. Diagonal entries have to be 1s and all other entries in the coefficient matrix of this augmented matrix to be 0s. So next, now let's go from this way now. To make this entries 0s, use these operations. So first row as it is, third row as it is, so only second row changes with these operations. So now we have 0s here. Next, we want to make 0s at this entry here. Perform these operations, then again second row as it is, third row as it is, now first row changes, now 0s here. So now next we want to make 0 at the place of entry 3 here. We use these operations. And we will get the final one here, the final matrix, all the diagonals 1 and all other entries in the coefficient matrix here the 0s. Then this augmented matrix is called the matrix in reduced row echelon form. So we're done. I hope this comes to make sense to you all. So now let's move on. Now part D, solve the systems. So here, when you have the matrix in reduced row echelon form, then this right hand side here, or the values or the entries in the constant matrix, these are the solutions. This corresponds to x values, this corresponds to y values, this corresponds to z values. So here x equals to -9, y equals to 13, and the unknown variable z equals to 12. These are the solutions of our systems. Great. Part E, solve the systems by triangularizing the augmented matrix and using the back substitutions. So that means we are using Gauss elimination methods. So the solutions, so to use the back substitutions, we want our matrix in row echelon form, that is upper triangular form. So this is the upper triangular form we obtain in part C. Then we need to convert this upper triangular matrix to a systems here, system equations. So here's, so x minus 2y plus 3z equals to 1. So from here, the x times 0 is 0, so start from y here. 7 times y minus 8z equals to -5. And from the last row here, this gives us simply negative z equals to -12. So now we have the systems here. So now to use the back substitutions from the last equation here, z equals to 12, z equals to 12, and then put the value of z equals to 12 in the second equations. So put z equals to 12 here and simplify. That gives the value of y, which turns out that y equals to 13, and put the value of y equals to 13 and z equals to 12 back in the first equations and simplify. This gives us x equals to -9. So our solutions are -9, 13 and 12. That's the same answer we obtained in part D here. In part D, we use the reduced row echelon form of the matrix, and in part E, we converted the augmented matrix to the upper triangular form and used the back substitution technique. We got the same answer. I hope this makes sense to you all. Great. So now let's move on. Now example 2. So solve the system of linear equations in two variables. So this time let's solve the two equations in two unknowns by converting the systems to upper triangular matrix and using the back substitution technique. Great. Solutions. First, let's write the augmented matrix. So here, this is the coefficient matrix, 2, 1, 1, -1, and this is the constant matrix, 1, 5. We are joining these two matrices, gives us the augmented matrix. Next, we want first entry is 1, so let's switch row 1 and row 2, which I did here. And the next we want 0 below the first diagonal entry. So to make here the 0, we perform these operations. We multiply the row 1 by -2 and add to row 2 and use that result to replace the row 2. So now which is here now. The first row as it is, and this operations gives us the new second row, which is 0, 3, -9. So how do I get 0 here? We multiply row 1 by -2, so -2 times 1 is -2, and add row 2. So -2 plus 2 is 0. Here 3. Let me check. -1 times -2 is +2, and then add 1, 3. Here is -9. Let's check this one. 5 multiplied by -2 is -10, add 1, -9. I hope it makes sense to you all. Next, we want the diagonal entry is 1, so now here we want 1. Then we use this operations. We divide the row 3 by 3. We divide the row 2 by 3. It's a row 2, it's a typo here. Then we will get 1 here, the first row as it is. So now this is the row echelon form. So now we need to convert this row echelon form or this upper triangular form to the systems here. So here we have y equals to minus 3 and x minus y equals to 5. Great. So now we have the values of y. We put y equals to minus 3 back to the first equations. Then this gives us x equals to 2. So we found the solutions of the systems 2, minus 3. Great. So I hope this idea makes sense to you all. So now let's move on. Example 3. Example 3. Solve the systems by triangularizing the augmented matrix and using back substitutions. So now we are solving this 3 by 3 systems. 3 equations, 3 unknowns using back substitutions. Let's begin the solutions. First, write the system in augmented matrix form. So here, this is the coefficient matrix, this is the constant matrix. Join those matrices and form the augmented matrix. So in the next, to apply the back substitution, we need to convert this augmented matrix into upper triangular form. So we want the diagonal entries 1 and below the diagonal entries 0. Here 0, here 0, here 0. So first, we want the first diagonal entry to be 1. So to make it 1, we simply switch row 1 and row 3 because row 3 has 1, the first leading terms here. So we did here. We simply switch row 1 and row 3. So the row 3 becomes row 1 here and row 1 becomes row 3 here. Row 2 as it is. I hope this makes sense to you all. Next, we want to get 0 here. So below the first diagonal entries, this 0 is already there. Now we want to make this 2 0. Then we perform this operation here. We multiply row 1 by minus 2 and add to row 3 and use this result to replace the row 3. Then this gives us here first row as it is, second row as it is, and use these elementary operations to get the new row 3. Now let me scroll this way. Now we have this one here. Oh, we have all entries in the coefficients matrix here the zeros. So that means the system is inconsistent because in row 3 this 0 is not equals to minus 9. So that means no solutions. Hence the system is inconsistent. I hope this makes sense to you all. So here's this one I mentioned earlier. Let me show you the note here. Oh, maybe here. Yep, here. So here, if all entries in a row of the coefficient matrix in the augmented matrix are 0, then the system is inconsistent systems. Great. So here we got all the zeros in the coefficient matrix in the last rows. Hence the system is inconsistent. Great. So I hope this makes sense to you all. So we finish these sections. Thank you.